Information gain. It's just another way of looking at mutual information, but it's a highly practical way of looking at it. So let's recall mutual information, all these properties. Its definition, total entropy minus joint entropy. So therefore it's the information shared or mutual between X and Y. It's defined by the Kullback-Leibler divergence of the joint probability and the product of the individual probabilities. This is what it looks like as a double sum formula. It's symmetric. The entropy of X with, the mutual information of X with itself is the entropy of X. It's between 0 and the smaller of the entropy of X and the entropy of Y. And it's 0 if and only if X and Y are independent variables. And it's also the entropy of Y minus the conditional entropy of Y given X. But what exactly do we mean by that? In particular, let's start with specific conditional entropy. That's the entropy of Y given a specific X. The entropy of the conditional probability of P of Y X for a specific instance of capital X. Let's get an example. Suppose F is a numerical feature and Y is in a set of labels 0 to C minus 1. Given some theta in R, we define X equals 1 if F is greater than or equal to theta and X equals 0 if F is less than theta. In other words, variable X has only two outcomes, 0 and 1. It's associated with the set 0, 1. We say that X is a decision rule on F. And the specific conditional entropy is for X true is given by this sum over the conditional probability of Y given that X equals 1, log base 2, again, conditional probability of Y given X is equal to 1. So let's go back to the conditional entropy. The entropy of Y given the knowledge of the variable X, first by noticing that little f of X equals the specific conditional entropy is a function of little x. Therefore, the conditional entropy of Y given the variable X is the expected value over X of the specific conditional entropy as a function of little x. Here we are as an expected value. So in an example, F in R and Y is one of C minus 1 label, or C labels. X is a decision rule on F. It's either true or false. And the conditional entropy of Y given X is therefore the sum where X equals 1, little x equals 1, plus the sum where little x equals 0. Written in terms of the decision rule, it's the probability of F less than or equal to theta given the specific conditional entropy of Y given F less than theta, plus probability of F greater than theta times the specific conditional entropy of Y given F greater than theta. So conditional entropy, we can write it as this sum, and there's the definition of specific conditional entropy. And we can then use the definition of conditional probability. We can interchange the sums, but now we can cancel those P of X's, and we can write our logarithm of the fraction as a difference of logarithms. Splitting that into two sums, we see that the first sum is the joint entropy, and the second sum, notice that we can sum over Y for fixed X, and that becomes the marginal distribution of X, and therefore we get H of X, that's the pure entropy of X. And that implies that mutual information is the conditional entropy of Y, is the pure entropy of Y minus the conditional entropy of Y given X. So this is what's called the chain rule for conditional entropy. The conditional entropy of Y given capital X is the joint entropy minus the entropy due to capital X. There are many different ways to write it. There's a third variation with 3 variables. There are many consequences and many applications of this chain rule for conditional entropy. Bayes' rule, the second form of the chain rule. And if x and y are independent, then h of the conditional probability of y given x is h of y, and the conditional probability of x given y is just h of x. So that leads us to the concept of information gain. That's the information gained about y due to our knowledge of variable x. And notice that the total information is the gain plus whatever we were given to begin with. So the entropy of y is the information gain of y given x plus the entropy of y given x. We can solve and get information gain as the entropy of y minus the conditional entropy of y given x, but that's just mutual information. So we have a key concept. Mutual information is just another name for information gain. It's a hands-on interpretation of mutual information. It's between 0 and the minimum of the entropies of x and y respectively. And what does that mean practically? Well, we may not learn anything. We may gain no information. But how much we can learn is limited by the information that's available. So the information gain, that's how we've defined it. It's just another name for mutual information. It's a measure of how much we can learn about y once we've learned what there is to know about x. Back to our generic example. This time suppose we have n features, f1 to fn, all numerical, and that y is in a set of labels. X sub I is a decision rule on a feature f sub I of the data. The conditional entropy of y given x sub I, well, x sub I can only have two values, true or false, so this is what it looks like. The information gain is the entropy of y minus the entropy of y given x sub I, and that is the information gain from a decision rule x sub I applied to a feature f sub I. And we can think of this in terms of decision trees. So a decision rule is where we have x as a decision rule to a feature. That's our node. It can either be true or false. And we tend to explore the information gain of y given x for each feature f sub I of the data. For example, we might have a decision rule such as height less than or equal to 6 feet. That's true for some people, but false for others. The information gain of y given x is how much we learn about whatever y is from applying a decision rule like height is less than or equal to 6 feet. Decision trees have decision rules as nodes, and the terminal nodes are called leaves. And leaves collect information. So for instance, this is an example. If we had 40 positive and 10 negative, then we can predict that an observation reaching this leaf is positive with a confidence of 80%. And we can say that observations that end of the same leaf are neighbors. Leaf information can be used for either classification or regression, or many other things. The question then just becomes, how do you choose the nodes? Well, let's go back to our car evaluation data. One approach is to use information gain. So we have mutual information scores for price and maintenance, doors, persons, trunk, and safety versus grade. And we saw that the one with the most information was safety. But how do we make this a decision rule? Well, we have to have something that's either true or false. So we'll say safety equals high is either true or false. So our variables, G is the grade, S high is 0 if the safety is low or medium, and 1 if the safety is high. That makes it into a decision rule. Medium is 1 if the safety is medium, otherwise it's 0, and so on and so forth. So we've changed set membership into these decision rules. And we can look at the information gain, and we notice that the information gain of S high given G is the same as the mutual information of S high given G, which is 0.79 nats. So same thing with medium and low. And notice that you get the same information gain from a decision rule and its negation. So if low equals false, then medium or high is equal to true. And we can see that here in terms of our Python. So if we've got a mutual information score for safety being low, so our first note is that safety is low. And notice that our true leaf is 576 unacceptable. The rest are 0. But here we have a mixture of unacceptable, acceptable, good, and very good. 1152, where safety is medium or high. So looking at this kind of a distribution, we often use this bracket with these numbers indicating those numbers. And there it's not all 1. We say the true leaf is pure, and we decide, well, we probably should split this other leaf with another decision rule. So our goal is a classifier that predicts grades given other features. We look at our mutual information score again. We see that 2 people. If we have persons as 2, if that's true or if that's false, we get this mix. But if it's true, we get this pure leaf. And we can continue. And we can see that we have now 3 pure leaves and still have a leaf that has a mix. Maybe we'll want to split again, but let's just ask the question, well, how good is this? Well, if we start out with information of 0 nats, and the first is an information gain of 0.152, and the second 0.267, and the third 0.096, we add all those up, we get 0.515. But the actual Q distribution, probability distribution, looks like that, and its entropy is 0.84 nats. So therefore, we've gained about 61% of the information in this data with this tree that we have so far. So how well does the tree predict if a car is unacceptable? Well, now we're just going to look at the first of these 4 labelings, and we see that if the safety is low, it's unacceptable. We see that if safety is high or medium, but the price is very high, then we have a 62.5% Bayesian probability that this car would be predicted as unacceptable because of its high price. So here we can write some Python code to actually do this grading for us. And we can actually run through and make predictions. We can get our receiver operating characteristic, which has an area under the curve of 0.93. And then we could do the same for instance, is trying to predict if a car is very good. It's got a lower AUC. So this is not the only approach. Suppose we have a distribution like this before the decision, and distributions for false and true like this define these capital N's. Then you can show that the information gain at the node is approximated by this expression. And entropy is not the only function that maps a probability distribution to a positive real number. So we can actually use something like this. And in practice, F is not entropy. It could be classification error, could be Gini coefficient. And such a function, F, is called a measure of impurity. In summary, conditional information probability entropy refers to the fact that if Y depends on X, then the information obtained from Y may be reduced by the knowledge that X equals X is certain to occur, or the uncertainty in Y is reduced by knowing what Y is going to be, maybe not a specific X, but in general we know what it is. And information theory says that such reduction is in the form of a difference. In other words, the information gain is the entropy of Y minus the conditional entropy of Y given X. Mutual information.